Hello. Hello, students. Strange place to start, maybe. How fast? Well, what we've been talking about, my students have been talking about position and time graphs. And specifically, we're going to talk about position in meters and time in seconds. And what we said was, we know that for this graph, slope is velocity. All right. So we're going to show you, well, maybe for most of you, probably a refresher how to find slope, or at least for my guys, the practice I want to see you use when you are, well, finding slope, I guess. All right. So let's say you have a bunch of data points that look like that. And part of your job is to say, I recognize a trend in this data. That trend is linear, or that relationship that this data shows is a linear relationship, right? If that's the case, your job is draw a line of best fit. Not a line of best fit that starts at the origin. Not a line of best fit that connects the first dot and the last dot. A line of best fit. Now, this is for us a qualitative enterprise. There are quantitative ways of calculating linear regression, blah, blah, blah. I'm very happy with us when we draw graphs by hand, just making our best effort at it. Okay? So what this means is get it as close to as many points as you can. All right? Please don't jam it through the origin. Please don't just connect the first and last points. And it certainly wouldn't kill you to extend the line past each of the end data points. Now notice, I'm imagining this is my ruler. I'm sort of wiggling it back and forth to try to maybe have the same. I'm trying to get as close to as many points as I can. Fine. Okay. You happy with that? I am. Okay. So there's the drawing the line of best fit part. Now here's my ideal best case scenario. Once you do this, it would be awesome if somehow the data points themselves could just disappear. Because as of right now, we don't want to concern ourselves with data points ever again. They mean nothing to us. Their job is only to serve as a way for us to identify the general trend that this data demonstrates. And it demonstrates a nice linear pattern. There's our line. See you later, data points. I don't want to talk to you anymore. Because we are now equipped with this line to find its slope. And here's how you're going to do it. Well, I want to look for things like this. I'm not circling that data point. I want to look for things like this, and I'm not circling that data point. What I am circling is the fact that at this place, that line goes right through the intersection of the graph paper lines right there. And the same thing here. And the great thing is those points are pretty far apart. I would recommend against finding points that are close together that can, well, just don't do that. It's best if you can find them as far apart as possible. Okay? Now, if one of your data points is right on the line, can you use that? Sure, I guess. But again, I would rather we just didn't concern ourselves at all with data points once we've identified our general trend. Okay? So for us, the way we've talked about notation, this is point x naught. No, I'm sorry. It's actually t naught comma x naught. Right? In a Cartesian coordinate x, y sort of way. Right? So this is our initial time and initial position. This is our, whoops, that's a force of habit doing the x first, right? Here is our final time and final position. All right. As we know, as we defined, the average velocity of this object is delta x over delta t. Now that's why the slope is the velocity. Now I'm going to add in vector, vector. Oh, now what I haven't done is put numbers on my graph yet. oh, I don't know, let's call each of these, say, 20. So each line is 10, 40, 60. And let's call each of the, let's say like 1, 2, 3, 4, 5. Okay? Now, if we're going to do this carefully and really like, what's the word? Not completely, but thoroughly, sure. I would say that V is, well, the change in any quantity is final value minus initial value. Okay? So let's see, final value of position is 130. Initial value is 60. Agreed? Right? Yeah. Yeah. Final value of time, 5.5 seconds. Initial value, 1.25 seconds. 70 meters in 4.25 seconds. Average velocity is we'll call it, I'm not being careful with sig fig, sorry, 16.5 meters per second. What I should say is I hope you're not, it would be better if you weren't necessarily writing down these numbers, because your line of best fit might not have gone through the same points that mine did. I should have said that a minute ago. That would have been better, because we all have our own little interpretation of what the best fit is, and maybe your best fit line goes through different points than mine does. So you got to be careful up here about just blindly writing down what I'm writing, because again, your best fit line might not go through those same two graph paper intersections. But as long as you're careful, you're going to get very close to the same average velocity that I got. But you might have used two different points to get it. I hope that's the case for some of you. So if you blindly wrote down what I wrote, what you have to do is go back to your line O best fit and make sure that, well, really make sure you're identifying 2 points that actually fall on the line, and then see if you can get the same average velocity I do by plugging your coordinates into that, into our average velocity calculation. Okay? So, for my kids, my students, your job on your dune buggy lab is to go through this exercise for each case that you plotted on your position time graph. Calculate the average velocity of your dune buggy for each case. This is a full credit solution. I have an equation, well, even better equation. I've substituted values with their units into that equation. I've come up with the answer with the right units. Please provide a full credit solution. All right? Now, in general, what are graphs for? Right? Graphs are certainly for comparing variables, or identifying mathematical relationships. Right? Is there a direct relationship between the quantities on the x and y axes? Is there an inverse relationship? Is there a quadratic relationship? These are all relationships that we'll talk about as we go forward. Right? But as I said, what would be ideal, right, is that once we have data points, we use the data points to identify a general trend. and therefore a mathematical relationship in data, right? So you have to be able to identify some trends, all right? And the one that we've seen so far is this linear relationship between quantities, all right? So not a great slide. But the other thing, I guess, that graphs are for, as we've seen, is calculating some other quantity that aren't necessarily the things on the x and y axis. All right, so for our position and time graph, we now know we can calculate velocity. All right, graphs aren't just pretty pictures. There are ways to do this, identify trends and or mathematical relationships, and there are ways to do this, calculate something else. Find the value of something else based on a mathematical relationship between two other things. Okay? We did this full credit solution. Now, just so we're sure, okay, how do we know that for us, why can we be sure that for a graph of position and time, the slope is average velocity? Why does that have to be true? Well, for a couple of reasons. One is if we look at the equation, well, average velocity by definition is the rate of change of position. Well, where are we going to find that? Well, that's change in y value stuff. And where are we going to find this change in t? Oh yeah, well that's sort of a change in x value stuff. So this is the same thing as sort of saying, you know, generically on a graph, delta y over delta x. Oh yeah, that's slope. So since slope is delta y over delta x, but that's really change in position divided by change in time. Oh yeah, that is the equation for velocity. Yeah, that's one way to confirm what the slope of this line tells us. All right. The other method I like to use is we look at the units. Well, what would the units of slope be? Well, slope, again, right? Delta y over delta x, rise over run kind of stuff. Well, what are the units of the stuff on the y-axis? Well, that would be in meters. I always do, when I do square brackets like that, I mean units. So the units of the y stuff are meters. The units of the x stuff are seconds. Wait a minute, what has the units meters per second? Oh yeah, that's velocity. All right, so that's another way to tell that the slope of this graph is velocity. You can either use what's the equation that the slope would sort of give you, and two, what are the units that the slope would have to be in. And what I'm trying to do here is give you some tools for later as we go on in the year. We'll see a ton of graphs, and to be sure, not every single one of them has a slope that's equal to velocity. So what you can do on every graph you see is say, if I were to take the slope of this thing, what equation would that actually give me? Or if I were to take the slope of this thing, what units would that quantity actually be in? And therefore, you can do some deciphering as to what the slope of any graph really represents. Okay? Right. For my kids, my students, this is your assignment. You're going to find your cart's average velocity for each case. Draw a line of best fit. Line of best fit. Pick 2 points on the line. Write me full credit solutions and submit completed no later than then let's see, this will be tomorrow for you people. Yeah, so that's 9/18. That is 9/18. All right. Next time I see you. Okay?